Somewhere on the chip inside the device you're using right now, a single switch flipped on and off roughly 3 billion times in the past second. Not one switch. Somewhere between 10 and 100 billion of them packed onto a piece of silicon smaller than your fingernail, each one making a decision in less time than it takes light to cross a single room. Read that again. Every video you've ever streamed, every message you've ever sent, every game you've ever played, all of it eventually collapses down to the same absurdly simple question, asked billions of times per second by a device smaller than a grain of sand. Is the switch on or is it off? Everything else, every app, every operating system, every artificial intelligence model, is just an extraordinarily elaborate answer built on top of that one ridiculously simple question. To understand how something this simple builds into something as powerful as a modern computer processor, you first have to meet the actual switch itself, and it's genuinely nothing like the light switch on your wall. It's called a transistor, and at its core, it's built from 3 connection points: a source where electrical current enters, a drain where that current exits, and a gate, the control terminal that decides whether current is allowed to flow between the other two at all. Think of the gate as a gatekeeper standing at a doorway. Apply the right voltage to that gate, and an electric field forms, opening the doorway and letting current flow freely from source to drain. Remove that voltage and the doorway slams shut, blocking the current entirely. That's it. That's the entire fundamental mechanism. No moving parts, no mechanical components. Just an electric field opening and closing an invisible door over and over, billions of times per second, for years on end, without ever physically wearing out. This basic design, technically called a metal oxide semiconductor field effect transistor, has been the dominant building block of digital electronics since the 1960s and 70s, and even as its physical shape has transformed dramatically over the following decades, that core 3-terminal logic, source, drain, and gate, has remained essentially unchanged. Here's where this simple on-off switch starts becoming genuinely powerful. And it happens the moment you stop thinking about a single transistor in isolation and start thinking about what happens when you wire a handful of them together. Take just 2 transistors, one specific type paired with its electrical opposite, and connect them in a particular arrangement, and you've built something engineers call a logic gate, the smallest possible unit of decision-making in the entire digital world. The simplest of these is called a NOT gate, sometimes referred to as an inverter, and its entire job is elegantly, almost comically simple. Feed it a 1 and it outputs a 0. Feed it a 0 and it outputs a 1. It flips whatever you give it. This might sound almost too basic to matter, but it represents the first genuine spark of computation, the first moment 2 simple switches, working together according to a fixed rule, produce a predictable, useful outcome rather than just passing current straight through unchanged. From that single, humble inverter, engineers build progressively more sophisticated logic gates, each one performing a specific, well-defined logical operation on 2 or more binary inputs. An AND gate outputs a 1 only if every single one of its inputs is also a 1, otherwise it outputs a 0, the electronic equivalent of a strict rule requiring every condition to be satisfied simultaneously. An OR gate is more forgiving, outputting a 1 if any of its inputs happen to be a 1. There are variations built directly on top of these. NAND and NOR gates, essentially an AND or an OR gate, with an inverter attached to the output, flipping the final result. Here's what makes this entire family of gates so genuinely remarkable, and it's a detail almost nobody outside electrical engineering ever stops to appreciate. Every single one of these gates, no matter how sophisticated the logical operation they perform, is built from nothing more exotic than a small handful of those same humble on-off switches, wired together in slightly different patterns. The technology underlying almost every modern gate like this is called CMOS, short for complementary metal oxide semiconductor. And the specific genius of this approach lies in exactly how it pairs 2 different transistor types together. One type, called PMOS, conducts current when its gate voltage is low. The other, called NMOS, conducts current when its gate voltage is high. By carefully pairing these 2 complementary types together inside every single gate, engineers ensure that current only flows briefly during the actual instant of switching, rather than continuously leaking through the circuit the rest of the time. The single design decision, pairing complementary transistor types together, is precisely why your phone can run for hours on a battery rather than draining itself dry in minutes. And it remains, even in 2026's most cutting-edge chips, the exact same fundamental principle engineers relied on decades ago. Once you have logic gates, the next step up the ladder involves combining groups of them into slightly larger, more purposeful building blocks. And this is where computation genuinely starts resembling something recognizably useful, rather than simply flipping and combining ones and zeros in the abstract. Wire enough logic gates together in the right pattern, And you can build an adder, a circuit specifically designed to perform binary addition, taking two numbers, represented as strings of ones and zeros, and producing their sum as output. Nearly every mathematical operation your computer ever performs, no matter how complex it eventually appears on your screen, ultimately traces back to circuits built on exactly the same underlying principle, addition performed through carefully arranged logic gates. But computation alone isn't enough to build a functioning machine. You also need memory, some way to hold on to information over time, rather than having it vanish the instant the inputs change. This is where a different, cleverly arranged combination of logic gates comes into play, called a flip-flop. Unlike a basic logic gate, which simply reflects whatever its current inputs happen to be at this exact instant, a flip-flop is wired with a feedback loop, allowing it to hold a single bit of information stable, remembering whether it's storing a 1 or a 0, even after the original input that set that value has already changed or disappeared entirely. Group enough flip-flops together, and you get a register, a small block of extremely fast memory capable of storing an entire multi-bit value, the kind of number a processor actually needs to hold on to while it's actively working on a calculation. Combine enough adders, enough registers, and enough additional supporting logic gates together, and you arrive at one of the single most important components inside any modern processor, something called the arithmetic logic unit, or ALU. Think of the ALU as the actual mathematical brain sitting inside your CPU, the specific component responsible for genuinely performing every calculation and logical comparison your computer ever executes, whether that's simple addition, more complex multiplication, or comparing two values to determine which one happens to be larger. But even a powerful, well-built ALU can't function entirely on its own. It needs direction. It needs something telling it exactly which operation to perform, on exactly which pieces of data, at exactly which moment. That job falls to a separate component called the control unit, which functions almost like the conductor of an entire orchestra of transistors, fetching instructions from memory one at a time, decoding precisely what each instruction actually means, and then coordinating every other part of the processor, the ALU, the registers, the memory system, to actually carry that instruction out correctly. And running underneath every single one of these coordinated components sits a clock, a precise, relentless timing signal ticking billions of times per second, ensuring that every single transistor across the entire chip switches in careful, synchronized lockstep, rather than descending into complete electrical chaos. Layer all of these pieces together, transistors combining into logic gates combining into adders and flip-flops and registers, all of it coordinated by a control unit and synchronized by a clock, and you finally arrive at a complete, functioning central processing unit, the genuine mathematical and logical heart of every computer, smartphone, and server currently operating anywhere in the world. And the sheer scale involved here deserves real appreciation because it's easy to describe this process in simple, step-by-step terms without fully grasping just how staggering the final numbers actually become. Modern high-end processors and graphics chips now routinely contain somewhere between tens of billions and well over 100 billion individual transistors, all packed onto a single piece of silicon smaller than a postage stamp. Think about what that number actually represents. Every single one of those billions of transistors is still, at its absolute core, doing nothing more sophisticated than the exact same basic job described at the very beginning of this video, opening or closing based on an electric field applied to its gate. The staggering intelligence and capability of a modern computer doesn't come from any single transistor becoming smarter or more sophisticated than the transistor sitting right beside it. It comes purely from scale, from the sheer, almost incomprehensible number of these simple switches working together in perfect, synchronized coordination, each one contributing its own tiny fragment to a computation too complex for any human mind to track manually. Now, here's where this story becomes genuinely fascinating, because the physical shape of the transistor itself, the actual three-dimensional structure engineers etch into silicon, has changed dramatically over the decades, and understanding that evolution reveals exactly how engineers have managed to keep cramming more and more of these switches into smaller and smaller spaces, year after year, for the better part of 7 decades. The very first transistors used in digital electronics were built using what engineers call a planar design, essentially a flat switch, etched directly onto the surface of a silicon wafer, with the gate sitting on top like a simple layer. This basic, flat architecture dominated the entire semiconductor industry for roughly 50 years, continuously shrinking and improving, but never fundamentally changing its underlying geometric shape. Then, in 2012, Intel introduced something genuinely different at what's called the 22 nanometer manufacturing node, a transistor design called FinFET. Instead of a flat channel, engineers built a thin, vertical fin of silicon standing upright, with the gate wrapped around 3 of its 4 sides rather than simply sitting flat on top. Think about why that specific change mattered so much. Wrapping the gate around more of the channel's surface gives it dramatically better control over the current flowing through, reducing unwanted current leakage and letting engineers keep shrinking transistors, even as the flat, planar design was running out of physical room to improve any further. This three-dimensional fin design became the dominant transistor architecture across virtually the entire industry, powering every major processor generation from that 22 nanometer node all the way down to roughly 3 nanometers. But by 2025, even the FinFET's clever three-sided design had started running into its own physical limits, and the industry shifted once again into what's now considered a third distinct architectural era, called gate-all-around, or GAA technology. Instead of a fin with the gate wrapped around 3 sides, engineers redesigned the channel itself into a thin, horizontal nanosheet, and this time wrapped the gate completely around every single side, providing the most complete electrical control over current flow that engineers had ever achieved in a mass-manufactured transistor. Samsung's own 3 nanometer manufacturing process, developed in direct partnership with IBM, uses exactly this gate-all-around approach, sometimes marketed under the name MBCFET. And it represents the transistor architecture currently sitting inside many of the most advanced chips being manufactured anywhere in the world right now. And this brings us directly to the absolute cutting edge of transistor design, the genuinely remarkable breakthrough that connects directly back to the dramatic promise sitting inside this video's own title. In June of 2026, IBM unveiled something the company calls its nanostack architecture, achieving a manufacturing node the industry now measures at just 0.7 nanometers, or 7 angstroms, a genuinely new unit of measurement necessary because chip dimensions have finally shrunk down to a scale approaching the actual physical size of individual atoms themselves. The specific innovation making this possible carries the technical name complementary FET, or CFET, and understanding exactly what it does reveals a genuinely elegant solution to a problem that had been quietly limiting the entire semiconductor industry for years. Remember that complementary pairing described earlier, the NMOS and PMOS transistors that work together inside every CMOS logic gate to minimize wasted power? For the entire history of chip manufacturing up until this point, those two complementary transistor types had always been placed side by side on the same flat plane, consuming precious horizontal space on the silicon wafer. IBM's nanostack architecture does something genuinely different. It physically stacks one directly on top of the other, an NMOS transistor sitting immediately above its complementary PMOS partner, rather than beside it. Think about what that specific change accomplishes. By building vertically instead of purely horizontally, engineers can pack dramatically more transistors into the exact same amount of horizontal chip area. And according to IBM's own published research, this specific architecture delivers a 40% improvement in memory scaling, directly supporting the massive high-bandwidth data demands of today's advanced artificial intelligence workloads, while IBM's own roadmap projects at least another full decade of continued scaling built on top of this exact foundation. Before this story tips over into uncritical excitement, though, it deserves exactly the same honest, grounding scrutiny this channel applies to every genuinely exciting technical claim. Because the semiconductor industry itself remains genuinely, openly divided on whether this kind of continued scaling still matters as much as it once did. One detailed technical analysis summarized the current industry disagreement about IBM's specific announcement with striking bluntness, noting that if you ask NVIDIA, the company will tell you scaling in this traditional sense is essentially dead, no longer the primary driver of meaningful performance improvement. Ask TSMC, the world's largest chip manufacturer. And the company doesn't seem to consider the question especially urgent either way. IBM, alone among these 3 giants, lands firmly on the position that traditional transistor scaling still genuinely works, and still genuinely matters. Independent technical commentators examining IBM's specific announcement have also raised a genuinely fair, historically grounded concern, noting that IBM has a documented pattern of announcing genuinely impressive fabrication breakthroughs that other major manufacturers, Intel, Samsung, and TSMC, ultimately choose not to directly adopt, developing their own independent versions of similar underlying concepts instead. Some of these same commentators estimate that a true high-volume manufacturing implementation of complementary FET technology likely won't actually arrive inside consumer devices until at least 2031, and when it finally does arrive, it may well come from one of IBM's own competitors, building their own separate version of the same fundamental stacking concept, rather than from IBM's specific nanostack technology itself. IBM isn't the only laboratory racing toward this exact same 3-dimensional stacking frontier either, and a genuinely separate breakthrough, published in the prestigious journal Nature in May of 2026, tackled a related but distinctly different piece of this same underlying puzzle. researchers at the University of Illinois achieved something called monolithic three-dimensional integration of silicon transistors, essentially building multiple complete functioning layers of transistors, physically stacked directly on top of each other on a single chip. Here's the specific engineering obstacle this particular team had to overcome, and it reveals just how genuinely difficult this kind of vertical stacking actually is in practice. Traditional transistor manufacturing relies on a process called doping, deliberately introducing carefully chosen impurities into silicon to precisely control how that silicon conducts electricity. The problem is that conventional doping typically requires temperatures well above 600 degrees Celsius, and applying that kind of extreme heat directly on top of a previously completed, delicate layer of finished transistors would almost certainly destroy them entirely. The Illinois team solved this specific problem through a clever workaround, using what are called junctionless transistors, silicon, that gets uniformly heavily doped before the stacking process ever begins, entirely avoiding the need for any additional high-temperature processing once the layers are actually being assembled together. Using this approach, the team successfully fabricated 3 separate stacked layers, each one containing 625 individual transistors, and their results showed genuinely strong manufacturing uniformity and high yield, with electrical performance that matched conventional silicon transistors manufactured using the old high-temperature methods on ordinary, unstacked wafers. There's a third, genuinely distinct approach to this exact same fundamental challenge, one emerging not from an American technology company or university, but from Huawei. And understanding this specific approach reveals a fascinating divergence in engineering philosophy shaped directly by geopolitical circumstances. At a major semiconductor conference held in Shanghai in May of 2026, Huawei's semiconductor president, He Tingbo, unveiled something the company calls the Tau scaling law, proposed explicitly as a philosophical successor to the aging Moore's law framework that had guided the entire chip industry for decades. Rather than measuring progress primarily through transistor size, the way Moore's law traditionally has, Huawei's proposed framework measures progress instead through time, specifically the delay involved in signals propagating across a chip's internal wiring. The practical technology built around this philosophy carries the name logic folding, and it takes a genuinely different physical approach to the exact same underlying goal every other breakthrough in this video has been chasing. Rather than shrinking transistors within a flat two-dimensional plane, the specific approach, extreme ultraviolet lithography machines, are specifically built to enable. Logic folding instead folds traditional two-dimensional circuit layouts directly into three-dimensional vertical stacks, essentially, in the words of one detailed analysis, building skyscrapers directly out of individual chip layers. Think about the specific strategic logic embedded inside this particular choice. This approach explicitly does not require the kind of cutting-edge extreme ultraviolet lithography equipment that Western export controls have specifically, deliberately restricted China's access to, offering a genuinely alternative path toward improved chip performance that sidesteps that particular geopolitical bottleneck entirely. According to Huawei's own announcement, the company has already mass-produced 381 separate chips built using these Tau scaling principles, a genuinely concrete, already realized number, rather than a purely theoretical, future-facing promise. Even as these 3 parallel efforts, IBM's CFET, the University of Illinois' junctionless stacking, and Huawei's logic folding, all push toward extending silicon's useful lifespan through increasingly clever three-dimensional architecture, a separate, entirely distinct thread of research continues quietly asking a genuinely more fundamental question, whether silicon itself will eventually need to be replaced altogether. In August of 2026, researchers at National Yangming Chiaotong University in Taiwan published results in the journal Nature Electronics describing a genuinely different transistor material entirely, built from molybdenum disulfide, a material so remarkably thin it can exist as literally a single atom in thickness while still retaining genuinely useful electrical properties. Using a technique the researchers call epitaxial interface engineering, the team pushed this specific material toward a scale of 0.42 nanometers, an almost unimaginably small dimension, genuinely approaching the fundamental physical limits of what conventional matter itself can support. This research connects to a genuinely important, honestly acknowledged obstacle that has quietly haunted this entire category of ultra-thin, atomically precise materials for more than a decade. Researchers have repeatedly discovered that many of these theoretically promising two-dimensional materials mysteriously lose their most impressive electrical advantages once actually integrated into a working device, undone by subtle, previously invisible interface effects that only reveal themselves once engineers actually try building something real out of these exotic new materials, rather than simply studying them in careful theoretical isolation. Step back now and consider the full, remarkable arc this story has actually traced. From the simplest possible switch imaginable, a single gate opening and closing an electrical doorway, all the way up through logic gates, adders, registers, and a complete functioning central processing unit, and finally up to the genuine cutting edge of 2026's most advanced chip architecture, transistors physically stacked in 3 dimensions, approaching the literal scale of individual atoms. What makes this entire journey genuinely remarkable, more than any single specific breakthrough covered along the way, is the sheer continuity connecting its beginning to its current end. The exact same complementary pairing principle explained near the start of this video, one transistor type conducting when voltage is low, its partner conducting when voltage is high, working together specifically to minimize wasted electrical power, remains the literal unchanged foundation underneath IBM's most advanced 2026 chip architecture. The company didn't abandon that decades-old complementary principle to achieve its latest breakthrough. It simply found an entirely new, genuinely clever way to physically arrange those same 2 complementary transistor types relative to each other, stacking one directly on top of the other instead of placing them side by side. Read that again, because it's genuinely worth appreciating. The core electrical logic taught to first-year electrical engineering students explaining how a basic logic gate works is, quite literally, the exact same core electrical logic sitting inside the most advanced cutting-edge processor chip announced anywhere in the world this year. This is ultimately the deepest, most genuinely satisfying answer to the question sitting inside this video's own title. How do transistors build into a CPU? They build the exact same way an enormous cathedral gets built from individual bricks, or the way a single complex sentence gets built from individual letters through relentless, patient, hierarchical combination. A single transistor becomes a logic gate. A handful of logic gates becomes an adder or a memory cell. Enough adders and memory cells become an arithmetic logic unit and a set of registers. All of those pieces, carefully coordinated by a control unit and synchronized by a precise, relentless clock, finally become a complete, functioning central processing unit, capable of running the device you're using to watch this video right now. And even as engineers continue pushing that fundamental building block into increasingly exotic new territory, stacking transistors vertically instead of laying them flat, experimenting with entirely new atomically thin materials beyond silicon itself, the absolute core insight remains genuinely, remarkably unchanged since the very earliest days of digital electronics. Everything your computer has ever done, every calculation, every image rendered, every word displayed on your screen, ultimately traces back to the exact same simple, elegant question, asked billions upon billions of times per second. Is the switch on or is it off? If you want to understand exactly how these individual physical transistors actually get manufactured, etched atom by atom onto a silicon wafer, using the extraordinarily precise lithography machines covered across several of this channel's previous videos, that's precisely the story we'll be tracking closely next, so make sure you're subscribed before that deep dive finally arrives. Before you go, I want to know what you honestly think about everything you've just heard. Does the sheer, almost incomprehensible scale of modern processors, tens of billions of individual switches working together in perfect synchronization, change the way you think about the device sitting in your own hands right now? Or does the fact that the entire foundation still traces back to something as simple as a single switch opening and closing actually make the whole thing feel more understandable than you expected? Leave your honest answer down in the comments below, and as always, I read every single one.